So one of the many tools that computer scientists have at their hands is the recursive algorithm. And the recursive algorithm is used when you've got a large problem that the computer isn't able to solve all at once. So this is our big problem. And the computer just can't solve it all at once. Whatever it is, whether like multiplying two large numbers or finding a path, something like that. The computer can't solve it all at once. However, the computer is able to, if it had the solution to this big problem, this slightly less big problem here, it could figure out the solution to the whole thing using this solution and finding out this little part right here. And that's great, but we still have this giant thing that we need the solution to. And the computer says, okay, well, if I had the solution to this part, I could just figure this out and add it to it, and then I could add this part to that solution and find the answer. And so what you do is you keep dividing this large part until you get all the way to the bottom, or the base case as it's called, and the computer is able to solve that. And then it goes, great, I finally got the solution to this little problem here. I can use it to solve for this slightly bigger problem. And then once it has that, it uses it to solve for the slightly larger one, and so on and so forth, until it's able to build up all the way until we've got our mostly solved problem here. We combine it with the little bit left over at the top, and we found the solution to our larger problem by finding out the solution to many little subproblems and working up as we go. And an example of this that lends itself well to this sort of strategy is the Fibonacci sequence. So in order to calculate the Fibonacci sequence, we always add the two previous numbers to find the next one. So if the first two are by definition 1 and 1, the next one is 2, and then we've got 3, and 3 plus 2 gives you 5, 5 plus 3 gives you 8, 8 plus 5 gives you 13, 13 plus 8 gives you 21, and so on and so forth. And so you define this as the 0th one, the 1st, the 2nd, the 3rd, the 4th, the 5th, the 6th, and the 7th Fibonacci number, and so on and so forth. And so what we want to do is be able to calculate a specific Fibonacci number using our simple function. So if I want to find the Fibonacci number, let's say I want to find the 4th Fibonacci number. So in this case, the 4th Fibonacci number corresponds to 5. And how the program will do that is it has to find the solution to the two previous ones. So the 5th Fibonacci number, the 5th Fibonacci number is going to be equal to the 3rd Fibonacci number. So let's say Fibonacci of 3 plus Fibonacci of 2. So the 4th Fibonacci number, which I guess to be consistent, I will write it like that. Clean that up a bit so it's not completely messy. So I want to find the 4th Fibonacci number, and it's going to be equal to the sum of the 3rd and the 2nd. And now this is great, and so this is our big problem right here. We want to find the 4th Fibonacci number. And we need, in order to do that though, we need to find out the 3rd and the 2nd one. And so these are two slightly smaller problems. And however, we can't find the 3rd one until we find the 2nd Fibonacci number plus the 1st Fibonacci number. And the same deal with this. In order to find the 2nd one, we need to find the 1st Fibonacci number and the 0th Fibonacci number. And since these two are defined by definition, the 0th and the 1 are by definition 1 and 1, in this we could end up just returning 1 plus 1, or 2, and the same idea here, this one would return a 1, And this Fibonacci of 2 is the same answer as here. So this would be 2. So the Fibonacci for 3 is going to be 2 plus 1, or equal to 3. The second Fibonacci number is equal to 2. So we combine the answer we found here with the answer we found here, and we get 2 plus 3 is equal to 5. So we get the fourth Fibonacci number for 5. And so, as you can see, in order to find the fourth, we had to recursively go down into additional subproblems until we were able to reach problems that we knew the solution for by definition. So, these two are just defined by definition. And once we got to those, we used their solutions to build back up and eventually solve our big problem for the fourth Fibonacci number. And if instead of the fourth we wanted, say, the seventh, we would have had to go down recursively much further than this, but the same concept would have applied. Eventually we would get down to Fibonacci numbers of 1 and 2 and 0, and we'd have been able to build back up using these predefined solutions and get the final answer. And that's one of the important aspects about recursive functions, is you always have to have a base case. There has to be some small problem at the very bottom that you can get the solution for, and then use that to build back up. If there's no base case, then you end up just recurring forever, and you never get to a small subproblem at the bottom that you can solve and use to build back up. So, recursive algorithms are really useful for when you're able to divide the larger problem into smaller parts as you go, and solve a small problem at the very base and build all the way back up. If you can't do that, and there's no easy way to divide your large problem into smaller pieces and solve them as you go, then recursive algorithms probably not what you're looking for. Thanks.